Thomas Young's double slit experiment. In order to show you Thomas Young's double slit experiment, I used a laser. In 1801, did Thomas Young use a laser?
No.
Good, I'm glad you were able to identify that. Did he use a light bulb?
Maybe.
No.
We'll go with no on that one. What he used was a candle.
Only 18.
Put a candle in a box. This was his light source. So we know light is diffracted when it leaves. There was a single hole in the box. So light was diffracted when it left that single box. Now, he needed two coherent light sources. So he then put the double slit in front of here, and this creates two coherent light sources because they both come from the candle. They're both in phase with one another because they both originate from the candle. And therefore, we get two light sources that are in phase with one another. And you get this pattern that we just went through with the stop motion video. And you get constructive and destructive interference, and you get this, what is called an interference pattern on the screen. You get your alternating bright, dark, bright, dark, bright, dark, bright. Let's talk about specifically why and what they're called, all the various terminology. Let's see. So, this spot right here, where we have constructive interference, where we have constructive interference, we have a bright light, and that is called an interference maxima. Or the singular would be an interference maximum. That's the singular. Or if we have many, we have interference maxima for the plural. So all of these where we see the bright spots, those are called interference maxima for the plural, or we can talk about a single one. For example, the one in the middle is called the central maximum. Now, if we look here, you can see for the central maximum, the one in the middle, the length traveled by each of the rays from each of the slits is exactly the same. Therefore, the two are in phase one another, therefore we get constructive interference. If we go down to a dark spot, the first dark spot, the wavelength difference the path difference in terms of wavelengths traveled by each of the rays is going to be half a wavelength. Therefore, if the phase difference is half a wavelength, you get destructive interference. Going down to the first bright spot below the central maximum, the length traveled by the two rays from the slits has a difference of one wavelength. Well, we know one wavelength difference is going to give us constructive interference or a bright spot. So where we get interference maxima is where we have constructive interference, where we have a phase difference of one wavelength. Or any integer multiple, like 2 wavelengths, 745 wavelengths, right? Any integer multiple of wavelengths. Now, if you take a close look at the slit itself, the rays travel approximately parallel to one another. So they both have this angle here, theta, which is the same as this theta here when we make a triangle where the hypotenuse is d, the distance between the two slits. And this distance right here, the difference between how far these two rays traveled is d sine theta. So d sine theta is the distance, the difference in the distance traveled by the two rays from the double slit. Well, that needs to equal, in order to get constructive interference, an integer multiple of the wavelength. So it equals m times the wavelength, where m is equal to 0 plus or minus 1 plus or minus 2, so on and so forth, any integer. And m is called the order number. In other words, the central maximum, the one in the middle, has an order number of 0. The first maximum on either side is called the first order maximum, where m is equal to 1. This is going to be the first order maximum. This one right here would be the second order maximum, and so on and so forth. So if m equals 1, that's called the first order maximum. Just to get some terminology down. Again, this is for constructive interference where we see bright light. It's a bright fringe where we have a maximum. So let's just make sure m is clearly the order number, lambda is the wavelength of the light. What is d in this equation? Just to make sure we understand. Rudberg, what's d in this equation?
The distance traveled by the wave.
Actually, not the distance traveled by the wave, which is why we're going through it. It's not the distance traveled by the wave. What is d? Lindsay? Not the displacement. It's okay. Look.
Is it the distance between the two slits?
The distance between the two slits, right? Literally, when you look at this, it's going to be how far apart those two slits are. So you can imagine it's a very small number. In our figure here, we have each of our slits, and d is going to be the distance between the two slits. Technically, that is called the slit separation. But it is the distance between the two slits. What is theta? What is theta? Danner? Sure.
So is it
But what is this? That is the light has been diffracted, true, but that's the direction of the ray toward whichever maximum we're talking about, right? So this is between the direction of the ray and the normal. Notice how, again, this angle theta is measured with the normal. So it's the angle between the ray, the light ray going toward whichever order we're talking about, and the normal to the slits. Good. That was for constructive interference. Well, now we need to talk about destructive interference. For destructive interference, we need this. This is where we have an interference minimum. That again would be singular. Or interference minimum for plural. And let's see. So in order to get destructive interference, actually we should probably also put down here, this is called a bright fringe, sometimes called. This was called a dark fringe. In order to get a dark fringe or an interference minimum, we need a phase difference of what? Christine? Sure, in order to get total destructive interference, in order to get a dark fringe, a spot where we have a dark area, we need a phase difference of what between the two waves? A half a wavelength, right? A half a wavelength, or 1 1/2 wavelengths, so on and so forth. So the equation here is d sine theta equals m plus 1/2 times lambda, where again, m is equal to 0 plus or minus 1, plus or minus 2, so on and so forth. So yes, be aware that the first dark fringe above the central maximum is where m equals 0. Is where m equals 0, and it's called the 0th minimum. And then the first past the 0th order would be called m equals 1. That would be the first minimum, the first order minimum.